Hello, I want to do a show and tell of how I do kinematic analysis for this chair that I'm working on. And so this is the chair, this is the seat, and then this is the backrest. And I want them to be able to change it, to move. And I want it to be controlled with a linear actuator. So let me just show you a little bit of how I want it to move. Hey, looky here, woo. Um, so this is a simplified version. So this is the bottom piece. This is the seat, and then this is the backrest. Um, One of the positions that I want it to be able to go to is this nice and straight, laid back, and I want it to be able to sit up. Of course, you can do many others, like you can also recline. But the two extreme examples are sitting up and laying down that I want it to be able to do. So, yes, kinematic. So let me show you. Let's assume that I've already found the scissor mechanism that I want. Um, let's see, can I play with it? Yes. Let's say that I already found the scissor mechanism. So this is the piece here. And as it extends, it'll bring it up, and as it contracts, it'll bring it down. So those are the two positions that I want it to be in. If we've already found them, let's attach the actuator. Let me go in here and just choose some random numbers, mix it up a little bit. Okay. Ah! There we go. So as this is the actuator, and as it contracts, it gets shorter, as you can tell, and as the actuator gets longer, the backrest goes up. And by the way, this little V right here, these are the two different actuator sizes. So the first one is 337 millimeters long, and the other one is 515 millimeters long. So I want to find I want to orient this actuator in such a way that when this is perfectly flat, this actuator is at 337 millimeters, and when it is fully extended, I want it to be 515 millimeters. And so I can play with these. Okay, let's try 225, and let's try 625. All right, so, and then you can just, there's a bunch of different things you can do. You can try to solve this a bit more mathematically. You can find all the possible positions where you could put between here and here while it's flat, and find all the positions where you can put it between here and here while it's up. But that can be kind of math heavy, and I would rather just have the fusion geometric solver go ahead and solve that for me. So this is the example for if I've already decided where I want the scissor mechanism to be. Where would I put this? So that's what question this is answering. All right, so this is the similar example to what we had before. We have already found our scissor mechanism. So this is one set of the scissor mechanism where it's leaning up, and then this is the other scissor mechanism where it's leaning down, and this is the actuator. So that's the actuator while it's contracted, and that's the actuator while it's extended. And I need to somehow make Fusion 360 automatically, and just pretty much any CAD software will do this, but I'm just using Fusion 360 because it's convenient, where it will automatically find the perfect place to put this so that it's at the correct lengths to get these things where they need to be. So what I don't want, you may have noticed that this distance and this distance are different. So this is 150, this is about 300. So as it were to extend, it would be just pulling material and cutting through it. It would expect to be right around here, but for some reason it's over here. We can't have that. So what I do is, if I want to constrain a distance, I use a circle. So I know that this point, and this joint, of the mechanism are the same. It's just that at different times. This one is while the actuator is extended, and this is while the actuator is contracted. So if I put circles on these points, let me just make it easier to see, and I make these circles equal to each other, so now as I increase one, the other increases. And so the distance between, oh, put this on here, there we go. Oh, I already solved it, whoops, unsolve it. So the distance between here and here will always be 100, or at least the distance between this point and this point will always be the same between the distance between here and here. So as I put it onto this circle, boom, it automatically solves it and tells me where it needs to be. And in this case, it's 786, and the distance between these 2 points is 313. I know it can be kind of cluttered and hard to see, but if you let your eyes gloss over all of the construction lines, you can see the where it needs to be. So 313 millimeters and 786 millimeters. So just a scissor mechanism. Whoops, that's not right. There we go. So this was 786 and this was 313, I think. So now, as this becomes flat, we are at, so it needs to be 337, and that's just about 337. I think that's flat, 338, close enough. And then while it's inclined, we'll be at roughly 315. So yeah, that's about the same, the right angle. Yeah. So as it gets to there, it will be roughly 515, and when it lays down, it will be roughly 313. 337, sorry. So that's where that point would need to be. All right, so now, what if I need to solve not just the actuator position, but also the scissor mechanism angles, length, and position? So just all of the things. What if I need to solve for all of those at the same time? I'll give you a little demonstration of that. So all at the same time, let me hide this. So let me just show you my process for how it would be. It's a little bit involved, but I want my scissor mechanism. So that's the contracted, that's the extended, and let's just make it easier to see. All of these need to be the same length, so I will just do that. There we go. Now they're all the same length. A little bit wacky. I want the distance from this point to this joint and this joint to be the same. So I'm going to use a circle. That's a little bit hard to see. All right. So yep, now they're all on that. So now I need the actuator. Put the actuator down here. Put the first one there. Put the second one up there. And I'll use another circle. Actually, I'm going to make this circle easier to see. All right, so I want to constrain this distance. I don't want it shearing through material. All right, these should be equal. Yep. All right, so now the distance between here and here, 131, is the same between here and here, 131. So as the scissor mechanism opens up, those relationships stay the same. So now I need that to be equal and that to be equal. Now it's still not fully defined. There's still a continuum of possibilities. All right, I want to give you another example of a slightly more complex geometry. I'm going to put the actuator on the scissor mechanism itself. So let me make the mechanism. And of course, they need to be the same distance away from this center joint, or I guess back joint. All four of these members need to be the same length. Ooh. Make that all but easier to see. Allow me to fix this length just so it doesn't move around on me, and I'm also going to pin that in place. So that's how I want the actuator to be. It's going to be on the scissor mechanism itself. now we have to not just worry about the center scissor joint to the actuator end, but also the beginning as well down here. So I'll add that on, and then just make everything a little bit easier to see. So let's see, can I make this the right size? All right, that's fine. Goes up here. That's fine. And I will free this. There. All right. Oh, I forgot that these two must be the same length. There we go. Okay, so now I should have what's the word? Abstract kinematic design. So I can choose any of these locations and it will solve itself, or it'll break itself because there's technically a toggle point here. So there's all of these entire continuum of possibilities. I think there's two or three degrees of freedom. But let's say that for aesthetic purposes, I want this to be about halfway between these 2 points, these 2 lines. So I can manually put that here. Maybe you can imagine me constructing a line, saying it has to lie on that line. Another useful thing with this is measurements can be quite nice. So if I make a circle here, and if I dimension it twice, I can make a driven dimension. And we can watch this, we can try to optimize this moment arm. So for instance, whoa, I think this is still valid. If this moment arm was 600 millimeters and we wanted to make it bigger, we can actually just drag this and make the moment arm bigger. And the system will automatically solve itself. Or let's say we didn't care about this moment arm and we wanted this distance to be as small as possible. We can drag this over and try to find maybe where the breaking point. Maybe that's the breaking point. Watch out for toggle points. Let's say that this angle you want to know that it's no smaller than 35 degrees. Well, then you can solve it or matches for that. There's a whole host of different things that you can do with this. But so this is how I analyze my kinematic mechanisms.